Today we're going to talk about Unit 3.2, which is all about the theory of plate tectonics. So how did we come up with this theory of how our Earth is changing and shifting over time? So before we can get into plate tectonics, we got to talk about this guy, Alfred Wegener. I know it looks like it's spelled Wegener, but it's Wegener. Alfred Wegener was a meteorologist, actually, who kind of started noticing some clues about Earth and took a real interest in how we got to where we are today. So he studied in the early 1900s. He studied all about how our continents became the shape that they are into the locations where they are. He thought, okay, I think that at one point our continents were all joined together in this one big, massive supercontinent, and then they drifted to where they are today. So he had this hypothesis called continental drift, and that's literally what he thought happened. He thought that the continents drifted to where they are. He had some evidence. He had reasons to think that his hypothesis was correct. First of all, he saw that the continents were looking kind of like pieces of a puzzle. He also did some studies and found that there was evidence of matching fossils that came from across the oceans. And then he did some more research and noticed, hey, there's evidence of glaciers in these super hot areas, these tropical areas where a glacier wouldn't exist today, because glaciers are cold. But if these continents maybe were where it's cold and then they drifted to where it's tropical now, maybe that's a good explanation. So he had all these pieces of evidence, but he couldn't explain how these big, huge land masses drifted. And that was the problem. So Wegener proposed this hypothesis to the scientific community. He said, hey guys, I think that the continents drifted to where they are today. And the scientific community took his information into consideration and said, you're absolutely wrong. This did not happen. There is no way that these big, huge, giant land masses would have moved to where they are today. The way the Earth is today is the way it always has looked. You're crazy. Get out of here. So he was basically laughed off of the scientific stage. Not a good day for Alfred Wegener. So he wasn't really taken very seriously. He did have evidence for that the continents moved. He just couldn't explain how they might have moved. It wasn't until way after he died that the scientific community realized he might have been onto something. So this slide here is it's kind of a silly song about Alfred Wegener. Definitely watch it. It'll get stuck in your head. But it's pretty entertaining about him and his life. So as I said, Wegener did have evidence that the continents have shifted and drifted to where they are. First of all, his first piece of evidence is the shape of the actual continents. If you look at a map, it looks like those continents are pieces of a puzzle. It looks like, we can see it here on our screen. This is South America. South America could nestle right here into the little back of Africa here, and Europe and North America look like they could join together if you just put Greenland right there in the middle of them. So the shape of the continents look like the pieces of a jigsaw puzzle. And a huge clue is South America and Africa looking like they could just fit right in next to each other. That's a huge clue that Wegener was going off of. His next piece of evidence that he used were rocks and fossils. If you were to join those two continents, South America and Africa, in some of those common locations here, we have found fossils of common plants and animals. And so this is what we call an index fossil. So some of the same plant and animal fossils were found in these two completely separate continents that are oceans apart from each other. And the only explanation that Wegener could give for these fossils existing in just these two tiny places is that maybe these continents were joined. This animal lived in that area, and then that animal died and went extinct. And then once those continents drifted apart, the fossils of those animals drifted with the continents. A very, very famous example of this is the Mesosaurus. Right here, we have just a cartoon depiction of a Mesosaurus, but we have only found Mesosaurus fossils in these two very small areas of South America and Africa. And South America and Africa are completely an ocean apart from each other. But this animal he was not a swimmer. So a good explanation for how we could have them on two completely separate continents of the exact same animal, the exact same age, is at one point those two pieces of continents were joined. Mesosaurus lived in that area, and then after it went extinct and those continents drifted, those fossils went with them too. There's also some evidence of this is a tropical plant called the Glossoteris. Those are just some examples here that you might hear of. Another piece of evidence that he used to support his theory or his hypothesis of continental drift is that the rock layers in two different areas across oceans might be the exact same type and the exact same order and the exact same age, but they're completely oceans apart, and we know rocks don't swim. A good example of this are the Atlas Mountains in Africa and our Appalachian Mountains on like the east side of the United States. They're exactly the same. They're the same mountain range. They have the exact same order of layers with the exact same age of the rock, the exact same type of rock, and they're completely separated by the Atlantic Ocean. You can imagine this by thinking about making like a huge 20-layer cake, okay? And you've got a layer of chocolate cake on the bottom, and then a layer of strawberry frosting, and a layer of vanilla cake on top of that, and then a layer of caramel frosting, and then, imagine like 20 different layers of like totally random things. Maybe throw some chocolate chips in there. And then you cut the cake in half, and you send half of the cake to your aunt over in Maine, okay? The only way that this totally random person in Maine could get this exact same cake that you have here is if those two cakes were made at the same time in the same location, and then cut apart and moved across. Okay, so that's just another piece of evidence that Wegener used. Or you can imagine making like a really complicated sandwich and cutting it in half and sharing it with a friend. That's kind of what happened here, or what Wegener was saying might have happened. The last piece of evidence Wegener really focused on was climate evidence. He found research of tropical plants fossils being found in very, very cold Arctic and Antarctic areas. So tropical plant fossils, which would have really, really big leaves that require a lot of sun and a lot of rain, finding those kinds of plants all the way up in like Greenland or all the way down in Antarctica. Also finding glacier evidence, so those glacial grooves or striations or erratics found in areas that are very, very warm. So like places like India, which is pretty warm, not really a glacier heaven there. Parts of Africa, things like that, Australia. So the fact that he was able to do this research where people found evidence of glaciers in these very, very warm areas and evidence of these tropical plants in these very, very cold areas was a clue that maybe these continents weren't always where they are now. Maybe they've moved to where they are now. So maybe Africa wasn't always warm. Maybe Antarctica wasn't always cold. Maybe at one point they were kind of in a different position and they've drifted to where they are. So Wegener proposed this theory to the scientific community, and they said, absolutely not, because you can't explain how these continents would move. So then Wegener eventually died. And if you watched the music video, you know that he died on an expedition to Greenland. Um, and it wasn't until way after he died, like 20 years after, maybe even 30, I think the song says 30 years after he died, that the scientists started to study the sea floor. Okay, so we started to get some better technology. And when we got that better technology, we were able to actually map out the ocean floor. We can map out the ocean floor by sending sound waves down to the bottom, letting them bounce back up to the top, seeing how deep the ocean floor is. Well, we noticed that there's actually some stuff going, like the ocean floor is not flat. There's some mountain ranges in the ocean. There are these big rift valleys, and there are these huge deep ocean trenches in the ocean. And it's a really, really crazy dynamic place. And maybe Wegener was onto something. So after Wegener died and after we got better technology, we were able to come up with the theory of plate tectonics. Okay. Wegener's idea was called a hypothesis because it was never developed fully into a theory. Plate tectonics is a theory because plate tectonics can explain why and how our continents actually move. So the theory of plate tectonics tells us that the Earth's lithosphere, so our surface, is made up of these big, huge tectonic plates. And those tectonic plates sit on top of the asthenosphere, which, if you remember from 3.1, it's kind of like a silly putty or Play-Doh consistency. It's a semi-solid. That asthenosphere kind of shifts and moves and changes over time. And as that asthenosphere shifts and moves and changes, the lithosphere on top of it shifts and moves as well. So this is why we have the movement of our continents. This is why we have earthquakes, why we have volcanoes, and how we get the shape of our landforms that we have here today. So what evidence do we have for this theory? First of all, seafloor spreading. Okay, so our ocean is actually changing its shape all the time. So the continents aren't actually drifting. They're not like sitting on top and like floating along. They're actually part of the crust. But the crust has some different things going on here. Inside the oceans, in the middle of the oceans, we have what we call mid-ocean ridges. Mid-ocean ridges are these big, huge underwater mountain chains where two tectonic plates are pulling apart from each other. Those tectonic plates pulling apart from each other is going to leave room for magma to come out of the ocean floor. Once magma comes out of the ocean floor, it's going to shove those plates even farther apart, which is going to spread the ocean floor wider. That is the concept of seafloor spreading. That's one of our main driving forces of our continents drifting and moving to where they are now. And they're continuing, they're still moving today. We also see evidence of this happening in the ocean floor in the form of magnetic reversals. So magnetic reversals are kind of a mystery to us, but we see evidence of them happening in our ocean floor. Basically, what's going on is that we have magnetic minerals in our mantle, in that magma, liquidy, molten rock that comes out of the mantle. Those magnetic minerals, when they come out of the ocean floor at that mid-ocean ridge, when they come out of the ocean floor, they're still kind of molten. They want to line up with our Earth's North Pole, our magnetic North Pole, just like a compass, okay? So our magnetic minerals line up with the North Pole. What we see in the ocean floor, though, is that after that rock hardens, those minerals are stuck there. It kind of like freezes them in time. But what we see are stripes of minerals that are pointing north, and then a stripe of minerals that are pointing south, then stripes of minerals that are pointing north, and then stripes that are pointing south. And the only explanation that we can think of is that our magnetic field has actually flipped several times throughout Earth's history. It's a huge mystery why and how this happens. We just see evidence that it does in the ocean floor, in those stripes, those magnetic reversal stripes in the ocean floor. This here is a short clip from a show that Bill Nye did called Greatest Discoveries. He is going to go through how we know magnetic reversals have happened throughout Earth's history. So please watch that, and it should be linked in your notes. Another piece of evidence that we have that supports the theory of plate tectonics is the sheer location of our earthquakes and volcanoes. We see most of our earthquakes and volcanoes happening at plate boundaries. Yes, sometimes we have earthquakes and volcanoes that happen within a plate, so in the middle of a plate, but for the most part, most of our earthquakes and volcanoes and tectonic activity happens on plate boundaries. In fact, there is this area, and it's called the Ring of Fire, even though it's kind of shaped more like a horseshoe. But it's called the Ring of Fire. And the Ring of Fire is this area all around the Pacific Ocean where we have a ton of volcanoes and a ton of earthquakes. Actually a lot of not mid-ocean ridges, I'm sorry, a lot of deep ocean trenches and a lot of old volcanic mountains as well. So this Ring of Fire is all up along the coast of South America, all up along California, where we have the San Andreas Fault right here, Washington and Oregon, where we have our Mount Rainier and Mount St. Helens. We've got Alaska going on here, all the Aleutian Islands. We've got Japan, the Philippines, all kinds of stuff happening along this Ring of Fire. And that's because this is a very active plate boundary. What causes these plates to move is what we call mantle convection, or convection in the mantle or in the asthenosphere. This is the driving force of plate tectonics. So basically, the inside of the Earth is very, very hot. And as stuff gets hot and as stuff gets heated up, it needs more room. The molecules in that stuff needs more room to run around and move around because they're hot and they have a lot more energy. So as those molecules need more room to run around, that material gets a lot less dense. So as stuff becomes less dense, it floats towards the surface. And then it gets towards the surface where it cools down. And as it cools down, it starts to harden. And it starts to get more dense. And it sinks back down towards the bottom. And then it gets hot again because it's towards the center of the Earth. It's closer to that heat source. And it rises up towards the top. And then it cools back down and sinks back down towards the bottom. Those are what we call convection currents. So here we see this is a whole process happening here, convection currents. This is the same thing that happens inside a lava lamp. If you've ever seen a lava lamp, and I have one in my classroom that I'll usually keep on throughout the most of Unit 3. If you've ever seen a lava lamp, then you know the heat source is the light bulb at the bottom, and that's going to heat up the wax that's inside that lava lamp. It's going to make it go towards the top, and once it cools down, it's going to sink back down towards the bottom, heat back up, float towards the top, sink back down towards the bottom. So if you are in class and you see my lava lamp, definitely take a minute to watch the material that's inside it, because that's showing exactly how convection works. There are also two other processes called ridge push and slab pull that drive plate tectonics as well. Ridge push happens at a mid-ocean ridge, so that's why it's called ridge push. So the mid-ocean ridge is this big underwater mountain range where we have these two plates that are moving apart from each other. while stuff, material, magma is going to come out of that mid-ocean ridge and shove it out of the way. It's going to push it out of the way at the ridge. That's why it's called ridge push. So as a new material comes out of that mid-ocean ridge, it's pushing it out of the way. So it's pushing those plates along their path. Then we have slab pull happening on the other end. So way, way, way down on the other end of that plate, we've got some room for that plate to start sinking into the ocean. As that, or not into the ocean, I'm so sorry, but into the mantle. As that plate is sinking into the mantle, its own weight and the gravity of the pull of gravity pulling down on that plate is going to continue to pull that plate into the mantle. There's a video that I believe, oh, it's this one here. There's a video on the next slide where they kind of equate that to, like, if you can imagine a chain hanging off the end of a desk. Eventually, enough of that chain might be hanging off the end of that table or that desk where the weight of that chain will pull the rest of it off with it. Or you can think of it like a roller coaster cresting the top of a hill. When it's at the very, very top of the hill, the roller coaster's kind of resting there, but then eventually enough of that roller coaster crests the hill that the weight of what's hanging down here is going to pull the rest of the cars down with it. That's slab pull. So again, this video is going to talk to you about plate tectonics. It'll talk about ridge push. It'll talk about slab pull. It won't use those terms necessarily, but definitely give it a watch. This is a great, great, great summary of how plate tectonics works. So why do we care about plate tectonics? Well, I mean, I feel like it's pretty self-explanatory, but we should really care where we're at risk of earthquakes and volcanoes, right? You want to know if you're in an area where there's a high risk of earthquake or volcano or some other kind of tectonic hazard. But also, we want to be able to locate some valuable mineral deposits. So there are these places inside the ocean where we've got these minerals coming up to the surface from the inside of our Earth. And if we know where those are, we can use them to harvest and then use them as resources as well. Plate tectonics is really cool because it really unifies like a ton of different areas of science. You know, plate tectonics is going to bring together geologists with paleontologists talking about, you know, the locations of these historical fossils. And it's also going to impact where people and societies might choose to build or not build a city. It's going to also help us predict what will happen in the future. So the fact that we're able to know where we came from, so that big, massive supercontinent that Alfred Wegener hypothesized about, the fact that we know now that he wasn't wrong, and that our continents really have moved to where they are today, we can kind of take a look at where they're moving and predict where they're actually going to. And it helps us understand how we got the landforms that we have here today and how certain events have happened throughout Earth's history. Okay, so this is our very last slide here. Again, just summarizing the whole theory of plate tectonics. It's another short video. Definitely give it a watch. Very, very helpful information. All right, so that is all of our 3.2 notes on the theory of plate tectonics.